stop sharing. All right, so let me know when I can start.
Okay. Well, let me, if it's okay, let me stop the screen share because I always got to do the intro and stuff. I'm just waiting for Jeremy Reese to let me know.
So do I need to stop the screen? Because it looks like.
Oh, you know what? I can do it. I'll stop sharing there. Okay. And it says, okay, we are live. So let me do this. I'm gonna put this on speaker mode. Give me 2 seconds, and then I will do my intro just like normal, and then I'll hand it over to you, sir.
No worries.
Okay, there we go. So I think everybody can hear me. So what I'm going to do is, I think we're rolling. So in 3, 2, 1. Welcome to APEC. It's April 9th, and I'm your moderator, Tim Ventura. I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. So in today's session, Riccardo Storti will present on variable speed of light cosmology. John Brandenburg is going to be discussing GEM theory, and Ross Small is going to be demonstrating his RBI machine propulsion device. We're also going to have Mark Sokol and Falcon Space provide detailed lab updates and the results of their latest experiments. And we're going to be finishing off the event with open discussion and at least one ad hoc presentation by conference attendees. So just a couple of quick reminders. You can view those conference replays, details, and speaker info on our website at www.altpropulsion.com. Please save your questions for the Q&A session after each presentation. You can raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. You can also type those questions into chat, and we will go through those after each presenter finishes. Okay, so I want to introduce you now to our first guest. Riccardo Storti is going to be discussing variable speed of light physics and the implications that this offers for cosmology and reactionless propulsion. He's going to analyze a variety of important concepts in cosmology and discuss how our assumptions about the universe change in a VSOL model of physics. So let's welcome him to today's event. And now I will hand it over to him to get started. Okay, so Riccardo. There we go, sir.
Okay, so good to go. I just do a screen share now.
Yeah, no, we are perfect. Okay, and I'm going to spotlight you for everyone. I have everyone else muted out, and I can see your thing.
Great, good stuff. Thanks for that, Tim. Appreciate it. Okay, good day, everybody. Look, I'm going to start. What you see now is a slide just that says high-level presentation. I've actually prepared 2 versions of what you're going to see. This is the high-level version, so the short version to try and fit into my slot here without too much effort. But however, if we do have time, I will go through a more detailed presentation. It's got a bit more information in it. All right, so let's start. So the title of my presentation is Cosmological Compliance Testing of Electromagnetic Propulsion Solutions. So what this whole thing is about is, in a nutshell, to start off with, and I'll come to this soon, the presentation's about putting forward evidence that I'll show you for the requirement for 2 tests, so a GR test and what I'm calling a dark energy horizon test. So that's what the presentation is about in a nutshell, and I'll kick into it now. So point number 1 there, Miguel Alcubierre provides a solution to faster than light propulsion within the boundaries of GR. So many of you know Miguel Alcubierre. He's got quite a name for himself these days because of the work that he did in the early 90s. I think it was, where he proposed the idea of if you contract the space-time in front of a craft and expand it behind the craft, and you kept everything inside that bubble obeying GR, then you could actually travel faster than light. Now, the Alcubierre solution has issues which have been widely discussed and debated for many years. However, our focus in today's presentation will be answering the question, is the speed of light of a warp bubble constrained by some kind of cosmological limit? And as I mentioned before, the answer that I believe is yes, and I've termed this the dark energy horizon. So the first result that comes out of the research is that a maximum permissible warp speed is 1.1 c. So yes, warp speeds are possible, but not what you see in Star Trek. And the reason for that is because of what I'm calling the dark energy horizon. So the result coming out of this research is that all EMP solutions must be cosmologically compliant by passing two critical tests. So the first critical test I mentioned before is general relativity, and GR, I've got to stress to people, is it works on the astronomical scale. So it's an astronomical scale compliant test, and it works very well on the astronomical scale. However, we also find that we need a second test, and that's what I'm calling the dark energy horizon test, and that works on the cosmological scale, and it's a cosmological scale compliance test. Now, why do we need to answer the question above? Well, it's because GR is only about 4 to 5% successful on the cosmological scale. So 95 to 96% of the physical universe was not predicted by GR, nor is it described adequately by GR, because it misses things like dark energy and dark matter. The example for that is that the cosmological constant within Einstein's equation was intended for a static universe, not for an accelerating universe driven by dark energy. And the cosmological constant, as stated by Einstein, is in fact, as the name suggests, a constant. There have been, you can find work suggesting that it's related to dark energy. No one knows for sure, but that's the primary candidate these days. And even so, the current belief, the standard model of cosmology belief, is that even dark energy is a constant input into that cosmological constant. Now, the Alcubierre solution is primarily reliant upon GR. Therefore, if GR is 95 to 96% incomplete, it follows that the Alcubierre solution is also 95 to 96% complete. Next slide. What does the solution look like? Well, look, lambda, which is the cosmological constant, and c are not constants. They have evolved over cosmological time, as described by what I call EGM. And I'll speak a bit more about that in just a moment. Now, at the moment, c is a definition, and that is really, really important for everybody to hang on to this. The speed of light the speed of light in a vacuum is a definition. It is not a measurement. It used to be a measurement, but it is no longer a measurement. It's a definition. And what I'm saying is that that is only valid at the cosmological event horizon. Everywhere else in the universe, it's in fact less than c relative to that definition. And the reason why it's c only at the cosmological event horizon is because it is the only place or boundary in the universe, is probably a better way to describe it, that actually where space-time actually is flat. Everywhere else in the universe, space-time is curved. Even the addition of a single photon in the most deepest, darkest reaches of space somewhere, and you're a long way from everything else. You add one photon to it, you're curving space-time. So that's a really important point that I wanted to deliver to everybody quite forcefully. The cosmological event horizons should not be confused with the dark energy horizon, and that's what I'm proposing here. The dark energy field is a massive photonic field. That's what I claim it to be, and therefore can't expand at a rate of c. It expands at a rate of what I've labelled there h sub phi. The normal way to represent that would be h sub 0, so Hubble's constant, but the speed of light at the dark energy horizon, I'm saying, is 0.92 c. So it's not quite c, it's just below c, and it's just below c because the dark energy field is a massive photonic field. And if you read one of my publications on Hindawi, you'll see that I put forward a very persuasive argument for exactly that. Anyway, any physical measurement of C in the laboratory is merely an approximation of its defined value for a flat space-time manifold. So, as we all are aware of, experimental uncertainty, it's with us all the time and everywhere, and there is in fact no way that we can ever verify by experiment the defined value of C. So there's always that question mark hanging around. Now, if you look at that, that representation there, what you'll see are three circles. The black circle represents the expansion of the cosmological event horizon, and the speed of light at that boundary is the defined value, and we all know what that is. Now, the rate of expansion, h sub phi, is Hubble's constant. That's my calculation of Hubble's constant, and you'll see it's very close to the standard model of cosmology value. And I'll come back to that a bit later on because there's some important information around that. The red boundary is, red circle is the expansion of the dark energy horizon, and that's where I'm saying the speed of light is 0.92 c, and the blue region represents the expansion of the observable cosmological horizon, and the speed of light there, so for us, is 0.84 c. And the rate of expansion is 67. So the rate of expansion is constant across all of that naturally, as you might expect. Now, moving on. I should also point out that I've also labelled there between the red and the black boundary. That's flat space-time, and the dark energy field is what I'm describing here as quasi-flat, and the blue region is curved space-time. And it's important that everybody consider, pardon me, that in GR, what we tend to do, and using black holes as an example, what we do with GR, and what we can only do with GR, is stand somewhere outside the black hole and look down. Whereas in cosmology, you're at the bottom of the gravity well and you're always looking up. So we need to make this important distinction, operational distinction between GR and cosmology. So I just wanted to point that out because it's something that I keep forgetting to pass on. Okay, here we've got a solution architecture representation. So at the bottom of the pyramid, you've got general relativity. On top of that, I'm a big fan of the polarizable vacuum model of gravity. And then on top of that, you've got zero-point field theory. Pardon me. To the side of that, you'll see along here electrogravimagnetics. Now that's a methodology that's been developed by myself and Todd Desiato, and there's been significant success in that space in describing lots of things in particle physics around the mass and size of fundamental particles. We develop exact solutions for fundamental particles, notably the proton and the neutron, both of which have been experimentally verified to great precision. So it's pretty difficult to poke holes in that when it all lines up with experimental observation. And I've sort of taken that particle physics stuff the next step up using BPT. Now BPT is Buckingham Pi theory, and applied that to cosmology. From that, I've then been able to do two things simultaneously: derive the time history of the cosmological constant, and also the time history of Padov's refractive index. From that, I can then get the variable speed of light, and made sure that when that all happened, that it lined up to the cosmological constant, and it does. And validated that against standard model of cosmology derived value of cosmological constant. So there's a bit of a pathway there, but as I'm hoping you'll see, it's been worth the effort. Okay, so I mentioned, pardon me, electrogravimagnetics. So that's the key really to all of our particle physics stuff and my cosmology stuff. And the question then comes is, can EGM be trusted? Well, yes. You know, I'm biased, but yes, and because. Now, point number one, it successfully derives 30% of the information listed in the particle data group 2021, and it's not just 2021. I mean, the 2021 results are the same for a number of years now. Astrophysical constants and parameters, right? So, for example, the particle data group publish in 2021 published a Hubble constant value of 67.4, and I derived 67.1 something. You can see it on the previous slide. Now, just to emphasise that, I'll just put up on the screen here at the moment. So here we've got the astrophysical constants and parameters. This is 2019. But the results are the same as 2021. It's just that I happened to mark this one up in the 2019 when it came out. So what I've done here is I've highlighted all of the parameters that I'm actually able to derive to greater significance, greater precision than the particle data group. So my results align with all of their results, but I actually take it a little bit further. Now, as it works out, all those highlighted regions works out to about 30% of what's actually on this. So that's just the first indication that EGM can be trusted. It's not the last, it's just the first indication. Now, the second point here is EGM successfully derives experimentally verified solutions to particle physics challenges. Well, that's what I talked about before. There's a link there, and if you download, by the way, I made sure that, so if you guys want to, or people want to download the actual file, all those links should work. I went to great effort to make sure that it worked because I did have some problems. So anyway, if you click on these links, it'll take you to all of these documents. Now that's just point number two there. That published paper there. That's just one of a number of papers. It's not the be all and end all, but that does actually contain the exact solutions to the proton, neutron, and electron. And you'll see that the proton and the neutron align precisely with experimental observation to astonishing precision, I might add. Anyway, point number 3, it predicted the value of the Hubble constant. So this is something else that I want to crow about. In 2008, I predicted the Hubble constant. It's published in the links there. That's one. It's published in a couple of places, but that's one. That's the. I attended a physics conference here in Australia in Adelaide in 2008. So that's that first bullet point. That's where that's from. So that's officially in the literature. Now, I predicted this result 5 years in advance of experimental confirmation by the 2013 Planck satellite. So in 2008, if you look at these other couple of links underneath that, in 2008, the Hubble constant was reported by the particle data group as being 73 kilometres per second per megaparsec. So when my value came out at 67.08, I thought, oh God, it doesn't look very impressive. I thought, well, bugger it, that's my result, so I'm going to publish it, and that's it. I attended the conference and published it. Then in 2013, the particle data group, after the 2013 Planck satellite results came back, they published their result at 67.3. So it was a big jump by the particle data group to go from 73 to 67.3. And the reason it was 73 is because 73, in those days, before the Planck results, the Hubble constant was experimentally determined by looking at celestial objects, supernovae and stuff like this. In 2013, with the Planck satellite, it looked at the whole universe in one go. So that's why in 2008 their result was 73. And in 2013 it dropped down to 67.3. So look, I don't know whether any of you guys are much into cosmology or not. Not everybody is, I accept that, but that is no small achievement, I can assure you. Now, point number 4 is successfully derives experimentally verified solutions to cosmological challenges, and you can click on that link, and if you do, what you'll find is a paper that makes a prediction that I firmly believe is going to be verified by the James Webb Telescope, hopefully sooner rather than later. And that prediction is that the James Webb Telescope is going to observe and experimentally confirm that the universe is older than is currently believed. Now, the universe is currently believed to be 13.8 billion years old. I challenge that. I say it's in fact 14.57 billion years old, so 900 million years older than what it currently is. Now, obviously, when I say the James Webb Telescope is going to measure this, well, they're not going to measure it. I mean, no one's got a 14.57 or 13.8 billion year old clock that they can press the stopwatch on or turn it off. So the cosmological age is a calculation. It's not actually a direct physical measurement. But anyway, that's my prediction, and that goes against absolutely everybody and his dog. But I absolutely believe that that's going to be confirmed. All right, now the name of that paper that contains that is The Existence and Effect of Dark Energy Redshift on Cosmological Age. And you'll see in there, if you can be bothered or interested, how I calculate 67.118 kilometres per second per megaparsec. Now, that's an improvement on my 2008 result. And the reason I'm able to do it, and the reason why standard cosmology can't, is because I'm able to constrain everything that I calculate to the cosmic microwave background radiation. And the standard model of cosmology cannot do that. And for that reason, everything that they do is an approximation. Anyway, look, back to the variable speed of light solution. So what I've got here is my temporal solution for the cosmological constant. You can see two regions there. You've got a primary solution and the supporting equation. Now that's all an exact solution, right? So that's an exact solution for the cosmological history of the cosmological constant. So you can, plug those into your spreadsheets when you've got time and play with them and do whatever you like. But that's it. That's the evidence, and that is bang on correct. And I'd stand by that. Now, how can I say that? Well, look, here's the first little bit of evidence, and this is not what I would consider most convincing. Maybe someone will, but this isn't bad. I'm actually able to calculate there the value of the cosmological constant today. Now it's 0.79, say, and the standard model of cosmology derived value is 1.09, say, right? Now it's important for me to emphasize here what I've got there in the blue text in the box. The PDG value of lambda is not a direct physical measurement. It's a derived value based upon the physical measurement of cosmic microwave background radiation. Now, being a derived value, it is only relevant subject to the underlying assumptions within the derivation. Now, this means that the tolerance value in particular only applies to the set assumptions, and that's really important, right? The most obvious assumption is that lambda is constant by mathematical definition, as stated in Einstein's equation. Now, I'll also point to the fact that the PDG does not specify lambda to have a subscript 0, which is typically associated with the present day or present epoch. Now, something I'll point out, I want to mention about these numbers. Now, if you can see my T equals T sub phi result, 0.79, that's the present day. That's the value that I say the cosmological constant is today on Sunday, the 10th of April. Now, underneath that, you'll see T equals 3/4 T sub phi. Now, that's when that 0.935 is the result when the universe was 3/4 of its current age. Now, you'll see that both of those results are very close to the SMOC derived result. And in fact, in the detailed presentation that you can skip forward to in your own time, you'll see I'm actually able to produce stuff very close to that, to that red one there, to the PDG result, very easily. It's trivial. It's trivial, right? I can do it very, very easily. However, what I want to point out is that with my primary solution here, the present day result, say call it 0.8, it's very, very close to 1, but the 0.935 result is in fact even closer to the SMOC result, to the standard model of cosmology result. And the reason why I've highlighted that is because the derivation of that 1.09 result in the standard model of cosmology, we've got to remember that the standard model of cosmology, for them, lambda is constant. It doesn't vary. It is constant. So what I claim they have done is they've looked up in the night sky, they've made their observations, done their calculations, and what they have actually found is the maximum. Now, that T equals 3/4 T sub phi result, that is the maximum, that's the local maximum since I'm going to use a SMOC idea here. That's the maximum value of cosmological constant since the SMOC says cosmological acceleration began, right? That's why they get that result, right? So they get that result, they get their result for two reasons. One, they maintain its constant, right? I dispute that. And two, when they look at the night sky, what they're actually calculating, although they don't realize it, is the maximum value since about 7.3 gigayears. And 7.3 gigayears is when the standard model of cosmology says the universe started accelerating, right? And they're wrong about that as well, in my view, right? So what I'm saying here is that I'm right, they're wrong, basically, right? Okay, I'll move on to the next one. All right, so here we've got actually a plot of the cosmological history of lambda. Now, I'll draw your attention to this first graph up here. Now, along the y-axis here is the cosmological constant, and along the bottom line here, or along the bottom axis here, it's just time, cosmological age, right? So just ignore these arguments here, right? That's just my MathCAD way of representing time and here cosmological constant. So don't worry about that, right? Just look at the diagram. Now here you'll see that I've actually calculated when the Big Bang occurred, right? And that's at 3.6 by 10 to the minus 43 seconds, right? That's when the Big Bang occurred, right? So all of these are my results, right? They're all my results. So the Big Bang occurred here. The cosmological constant dropped down to 0. It crossed the axis, 0 at 5 by 10 to the minus 43 seconds. It then went negative to, now we'll jump over to this other graph here. It then went negative and stayed negative until a half of cosmological age. So it's 7.3 gigayears. So, and then at 7.3 gigayears, it was 0, lambda was 0, and then became positive after that. Now, this is actually really important, but I'll move through these results here. All right, so point number one, Big Bang occurred, then. It had a value of 1.25 by 10 to the 64. It was 0 at that time index. It was 0 again at that time index. And you've got to remember, I call it a half T sub phi. You've got to remember that's T sub phi, that's cosmological age. That's my cosmological age, right? It's 14.57 gigayears, which is the Hubble age, right? Standard model of cosmology says no, it's 13.8, right? So a half of my value equals 7.28. That's really important. Please remember that. Burn it into your brain, because I'll come back to that a bit later on. Lambda maximum occurs here, right? And that actually occurred at 10.9 gigayears, and it had a maximum value. That's what you saw on your screen before. So that's the maximum value over here. That's when lambda equals 0 here, the second instance. And the present epoch is 14.57 gigayears, and its true current value I'm claiming is that. Okay, now, is there any experimental evidence validating our solution? Look, good question. I'm glad you asked. And the answer is yes, because Fermilab assert that the universe began accelerating, and that's when Q equals 0, right? At approximately, now Q being the deceleration parameter, at approximately 10 gigayears. Now you can find it in this link here. You can go to page 44, and it's, I don't know, it's a few lines in. It's easy to find, right? Okay. Now we calculate that the deceleration parameter equals 0 at 9.6 gigayears. Now I should also say that not only have we calculated the cosmological constant, but also all of the standard model of cosmology's important parameters. So the dark energy density parameter, and sorry, I'm talking about also the time history of all of these things, right? So the dark energy density parameter, the matter parameter, and the deceleration parameter. So we've got time histories for all of these things, and they all line up with the cosmological constant, the values and the graphs and the behaviour that you're seeing now, right? Now, so keep in mind that Fermilab say that the deceleration parameter was 0 at about 10 gigayears. We calculate precisely 9.6 gigayears. So our calculation lines up exactly with Fermilab. So that's the first point, important point, good point. Here, the particle data group assert that Q equals 0. So they assert that the universe started accelerating, and it's, in fact, if you look at the particle data group sheet that I showed up before, it actually says that this is when the universe starts accelerating, right? Now, they say it starts accelerating at 7.7 gigayears, right? However, we show that the PDG 2021 Q equals 0 result is in conflict with Fermilab, right? So these two things are actually in conflict. They don't agree with each other. The correct interpretation of their result, that's of the PDG result, is that lambda equals 0, right? Now, we calculate that age as being 7.3 gigayears. That lines up just far too closely, far too neatly, far too nicely with the PDG result for it to be ignored, right? Now, the standard model of cosmology, by the way, does not, they are unable to calculate. I should stress this, because I just assume that you guys know what I know, and maybe some of you do, maybe some of you don't. So I may just tend to glance over things, but I should also stress that the standard model of cosmology cannot determine, they cannot calculate when Q equals 0. Right? They cannot say it happened at this time. No, I can do that. They can't do that. All right. So I just want to emphasize that. All right. Now moving on to the next one. All right. So the cosmological history of C. Now this is this is the money shot. This is what everybody's been wanting to hear about. All right. So once again, I'll just explain the graphs and I'll then move through these points. Okay. So here we have the Big Bang occurred. That's the time where it occurred. So it's the same as what's on the other graph. The reason why I have here the Big Bang occurring exactly at this axis is because in MathCAD, I couldn't put more than 2 vertical time markers here. So I had to set that one, I just set the boundary there. So just want to explain a bit of the difference why between this one and the other one in terms of formatting. Okay, so the y-axis here is speed of light operator. So what that means is I've basically just to make it easy, because the numbers can be very, very large or very, very small, and having the units hang on the end of it just makes it that much more cumbersome. I've removed the units so that when you see, for example, C equals 1, what that means is that C equals C. So C equals the speed of light. Right? If you see C equals, if you see it a half, right, then C equals half the speed of light, right? Okay. So the vertical axis here is the speed of light operator. And the horizontal axis is just cosmological time, cosmological age. I've got 2 lines here. I've got the red line, which is it's the EGM dark energy solo. So speed of light operator equals solo. Okay. Now the red one is so both of them are derived from the EGM construct, and that's why I say I make it clear EGM in the labeling. But I also do that because I can very easily flip between the standard model of cosmology's representation of anything and the EGM representation, right? So for me, it's very easy to just flip between the two. That's why I have to make that distinction, because I do that quite a bit in my solution algorithms. Anyway, so here at the instance when the cosmological constant equals 0, what we see is that the speed of light equals c at only that instant for the dark energy solo. So the blue line is the cosmological solo, so speed of light operator, and the difference between them is this: dark energy is explicitly dark energy and only dark energy. The cosmological operator, the cosmological solo, includes dark energy and matter and everything else, right? Includes everything, cosmological, as the name implies. And the reason why it's important to point that out is because the cosmological line also includes the contribution of dark energy, because dark energy is, well, dark energy and dark matter, it's 95%, not to 96% of all the mass of the universe, right? So I just wanted to point those two out. The blue line is the everything solution. The red line is the dark energy solution, solo only. Okay, now at T6 there, I'm not sure if I included T6 somewhere here. Maybe I didn't include it. But anyway, at T6, and if anybody's interested, I can give you the exact time for that. That's when the blue line crossed the c equals 1, so the speed of light equals the speed of light, you know, boundary there. Now on the right hand side here, we've got so firstly on the graph here on the left hand side, that goes up to 10 to the minus 42 seconds, I think, right? So the first 10 to the minus 42 seconds appears here on the left-hand side. On the right-hand side, top right-hand corner, we've got up to 10 to the minus 3.5 by 10 to the minus 22 seconds. So as you can see here, what happens is that actually rises up very, very fast. Now that's cosmological inflation. So cosmological inflation occurred from 0 up to this boundary here, right? And I've got the actual time, the actual instant in time when cosmological inflation stopped is that 7.78 by 10 to the minus 23 seconds. Now at that point, at that instant, the speed of light was 10 to the 38 times greater than it is today. Right, but and it's only instantaneous, and it starts decreasing from that moment on, right? But I wanted to highlight that. Now, what that does suggest is that because it existed naturally in the past, that if you can somehow study whatever the conditions are, whatever the conditions are at that instant in time, then in theory, if you could reproduce those conditions, you would be able to get much greater warp drive speeds than the 1.1 C I'm claiming is available to us today. All right. Anyway, you can see the numbers there. You can read them for yourself. It's pretty straightforward. Down the bottom right-hand corner here, we have the second half of the cosmological experience. So at this point here, at a half cosmological age, again, C equals 1 in the dark energy field and lambda equals 0 at 7.3 gigayears. So the standard model of cosmology, the PDG, they say that 7.3 is 7.7 plus or minus, a tolerance of 0 point something, or I can't remember, but you can have a look at that yourself, right? So again, that all lines up. So this number here lines up with the standard model of cosmology. This makes sense, at least to me, and this lines up with that. So I'll just cover off the points here. Now, utilising the polarizable vacuum model of gravity and our primary solution, so that's the equation you saw on your screens before, for lambda, we're able to plot the cosmological history, right? Now, the speed of light in the dark energy field is I'll call it 5%, right? So 9.5% higher than the speed of light in the baryonic field. Now, the baryonic field being, you know, you, me, us, all the matter in the universe, right? But in actuality, right, that also includes you know, dark matter as well, right? So anything that isn't dark energy, I've just, for brevity, labeled that the baryonic field, because that's what most of it is, right? Anyway, so the dark energy field is 9.5% higher. So the speed of light in the dark energy field is 9.5% higher than the speed of light in the everything else field, right? Now, what that implies, and I cover off this in the points later on, is that during at the instant of the Big Bang, the dark energy field actually started its journey slightly, just a moment in time before the baryonic field. So what's preceding us as our universe expands is a dark energy field, and we're moving along with everything else. This is what the dark energy field actually slightly precedes us. Okay, now, as I mentioned before, during cosmological inflation, the speed of light reached 10 to 38 orders of magnitude greater than today. The solo has equaled 1 twice in our cosmological history. So only twice in our cosmological history has the speed of light actually been c. Every other time it's been different. And the dark energy field solo, I'm calling that quasi-flat space-time, for the present epoch is 0.92 c. So because this is a solo number, it's just 0.92, but it actually means 0.92 c. And consistent with the diagram you saw before, in our cosmological observation, it's 0.84 c. Right. So all right, I'll move on, and yeah, just down here you can see where the present epoch is over here, and here you can see, I'll just, maybe you can't see that very well, but that's actually 4.6 gigayears. So in the cosmological solo, c equaled c at a cosmological age of 4.6 gigayears. Okay. Now, what's the lesson learned out of it? Out of this? Now, point number one: travelling faster than the local value of c is physically limited by the rate at which the universe's space-time fabric is expanding, and that's the number that I've calculated there. Right, consistent with all experimental observation. Right. If this were not the case, one could theoretically leave our universe after achieving escape velocity. Right, and this might introduce a paradox. So here's a calculation for the escape velocity, nothing new. You know, it's a few hundred years old. The actual calculations, I've just plugged in my numbers, right? So it's just 2gm on r, square root of 2gm on r, and I've just plugged in my numbers. So I've plugged in my calculation of cosmological mass. Again, in agreement with the standard model of cosmology, I've plugged in my value of Hubble radius length, and once again, that Hubble length is in agreement with the particle data group. If you look at their results, you'll see that my result is just it's bang on, right? Or rather, theirs is accurate compared to mine. That's the way I like to view it. Now, pi r, the observational radius or distance, again in agreement with the standard model of cosmology, and the observable universe, again that calculation is in agreement with the standard model of cosmology. You might see it listed or referred to as 92 billion, or maybe even 90 billion. Yeah, 92 billion light years or 93 billion light years, etc. But it's basically the same, and that's how you get it. Very, very simple, right? It's just basic circle stuff. The escape velocity, so what I actually calculate is that the escape velocity for our universe is the defined value of C. So it is exactly 2.999 by 10 to the 8. Right, so that, at least in my imagination, lines up well with what I might think. Being able to escape the universe would be a bit problematic, because that would then imply that mass and energy aren't conserved. Now, the speed at which baryonic matter travel, assuming GR constraints are also satisfied, is limited to the speed of light at the dark energy horizon. So if you remember what I had on screen before, our limit at the bottom of the gravity well looking up, our baryonic limit is 0.84 C. Sorry, that's what the value of C is for us right now, right? But the farthest that we can go is up to 0.92 C. But that's relative to the defined value, which is at the cosmological event horizon. To us, we measure C, right? So to us, it looks like C. It looks like C everywhere, right? But that's because our rules and clocks shrink. Okay, so lessons learned continue. Point number 2, GR is only 4 to 5% successful on a cosmological scale. 95 to 96% of the physical universe, when you include dark energy and matter, was not predicted, nor is it described by Einstein's equations. So simply put, and this is important, agreeing with GR is simply not enough. All right. Point number 1 there, 2.1. Consequently, it follows that a propulsion solution which satisfies GR only is insufficiently rigorous to be deemed cosmologically compliant. So saying that you've got a solution and it obeys GR, well, that's good. It's good. It's good, but it's not enough, right? Now, GR works well on an astronomical scale, but it does fail spectacularly on a cosmological scale. And I've wondered for a long time why I keep hearing statements about GR, it's very well tested. Well, it's not. It really, really isn't. And it's important that I touch on this as well. It's not. As an engineer, what's well tested are thermodynamics, the laws of electromagnetism. These are well tested. GR is barely tested. Anyway, that's just a debate for another day. So anyway, GR works very well, fantastically on the astronomical scale, but it does not work well at all on the cosmological scale. And the reason for that is the cosmological constant. And that's why I've spent so much time covering the cosmological constant here, is because we've got a fix for it. So when you plug our cosmological fix for the cosmological constant into Einstein's equation, that then fixes Einstein's equation so it is, so that it does describe on a cosmological scale things very well, and it works then on a cosmological scale and describes everything on a cosmological scale. But unless you do that, if you stick with what he's got, all right, with what Einstein put in there, it only works astronomically, where the cosmological constant doesn't really matter very much. Now, 2.2, all solutions for electromagnetic propulsion must be shown to be cosmologically compliant, as well as being GR compliant. So this is a critical requirement which cannot be avoided. So not only do you have to satisfy GR, you've also got to satisfy the dark energy horizon test. Now, cosmological compliance requires that the limit of the expected value of the electromagnetic propulsion apparatus, so its velocity, cannot exceed 9.5% of the local value of C. So that means that the fastest that you can go, the fastest that you can build your warp drive machine to go is 1.1 C. Look, that is, if you could do that, that's enormous. right? That is just a massive achievement, right? Not to throw any water on that. It's a massive achievement. What I'm just trying to communicate is that these Star Trek velocities, you know, warp 10 and the rest of it, and warp 13, I think, in one episode, it's not real. It's not physical. It's not even theoretically possible. Point number 4 there, the cosmological compliance condition is set by the speed of light at the dark energy horizon. And that's what I've been saying all along. And that this implies that the cosmological expansion of dark energy precedes cosmological expansion of baryonic matter, just, you know, by a fraction. Therefore, point number 5, breakthrough technologies at 1.1 C may not represent a practical means of interstellar locomotion, with the possible exception of our closest stellar neighbours. Summary, key takeaways. Point number 1, axioms of the PV model of general relativity. Right? Now, the definition of C is only a valid limit at the leading edge of our expanding universe, where the fabric of space-time, the fabric of the space-time manifold is perfectly flat. Right? So there's no energy there. It literally is nothingness. That's the only time that the speed of light, its definition, is actually applicable. Everywhere else, it's not. Now, where was I? Now, this is often termed the cosmological event horizon. So everywhere else in the universe, the space-time manifold is curved due to the presence of various forms of stored or transient energy. And that's what I was talking about before. As soon as you plop just one photon into a totally flat region of space, you've curved it, because there's energy there. You've added, you've curved it. Now, B, and this is really important, right? Now, the illusion of measuring C locally is maintained because our rules and clocks scale with local space-time curvature. So the reason why we always measure C as C, because this is something that people like to say, well, it's difficult to get people to understand, and Todd might agree with me on this, Todd Desiato might agree with me on this, that it's difficult for people to get people to understand that our rules and clocks, so what we use to measure C, are sitting in the same gravity well as what we're measuring. So everything has shrunk, has scaled, right, accordingly. So that's why we measure C as C. And I think I've presented some, I hope, persuasive evidence, experimentally verified evidence, as to why the idea of C not actually being C anywhere other than the defined, you know, around the cosmological event horizon. Hopefully that's persuaded some people anyway. So point number 2 there, experimental uncertainty precludes the possibility of exact confirmation of its defined value. So consequently, we necessarily assume that approximate equals exact, right? So we're never going to be able to actually confirm exactly that what we observe in the laboratory is the defined value of C. Point number 2, when applicable, all calculations should be constrained by the cosmic microwave background radiation. That's T sub naught. So what I'm talking about there is utilising, for example, the values of omega, Hubble constant, and cosmological time. So omega being dark energy density parameter, Hubble constant, cosmological time, the ones that I use, right, the ones that I've developed, which are constrained to this value here, rather than using the standard model of cosmology values, which are not constrained. And that's actually a significant area that the standard model of cosmology falls over. All of these values here are independent conclusions, and they're not constrained to T naught, which is very, very accurate. Anyway, you can read about that there if you want to, just follow the link. So point number 3, any viable EMP solution must satisfy the requirements of general relativity. So that is what I'm calling the first critical test. Moving on. Point number 4, the phenomenon of accelerated cosmological expansion is not explicitly addressed in Einstein's solution. I've talked about that ad nauseum. Consequently, at least one additional test is required when talking about when considering accelerated cosmological expansion, because Einstein's solution does not consider that. However, the reality is we live in an accelerating universe. So that's why Einstein's GR does not work on a cosmological scale, because it excludes that component. Now, the name given to this contribution is dark energy. That's typically what people are attributing the effects of dark energy to, is the 0-point field. So out of this, we get the second critical test, which I'm calling a dark energy horizon test. And this test involves calculating the EMP's solution, its local value of C. If the calculated value of C exceeds the expected value, or the expected value being the defined value, by the way, greater than 9.5%, right? So once you run your numbers in your design process or your investigation process, you run your numbers, and if you get a value of 2C, 3C, you expect your apparatus to be able to go, then you've got an issue. The most that you can go is 9.5%. If you're over this number here, then what you've come up with is not cosmologically compliant. It violates cosmology. Now, point number 3 there, therefore, the maximum local value of warp drop cannot exceed 1.1C, and I've repeated that a number of times. Now, point number 5, if the cosmological event horizon is expanding at an experimentally observed rate of Hubble's constant, it follows that to avoid some kind of paradox, there must be a physical limitation to how fast you can go. Now, if someone comes up with a solution of 200C, right, what that means then, if you think about it, right, what that means then is that if you travel far enough, at 200C, you can leave the universe, right? Its escape velocity, I'm saying, is 1C, right? And that's very very mainstream conclusion now, right? The escape velocity is C. All of those plug in my values. So that would violate the laws of being able to do that, would violate the laws of conservation of mass and energy, right? So the universe would be able to get fatter or get skinnier if objects were able to leave. So that would just break physics, right? And I just can't accept it as true. Finally, there, in addition, we've shown that the escape velocity for our universe is the defined value of C. Right. So look, that's it, viewers. That's the end of the high-level presentation. There are a couple of things in the detailed presentation which I can go over, which aren't included, which relates to Todd Desiato's radiative damping model. I did mean to include that, right? But feedback I got was that my presentation was just too long and could be complicated for viewers, so I chopped some of it out. And there's also some really groovy graphs and predictions that I make. Well, look, one prediction I will make just very, very quickly, right? And because I want this on the record, so I'll go to this graph here, and here's my prediction. So on the right hand side here is the standard model of cosmology. These are all the figures that I've derived, right? So all these results I've actually derived, right? So I've derived everything that's expected in the standard model of cosmology. right? On the left-hand side is I'm taking it one step further. I'm saying that actual dark energy composition is only 50%. It's not 67%. I can derive that 67% easy done, right? But what I'm saying is that 67% is in fact wrong. It's actually 50%, and that 17% is actually being misidentified, right? Because a bit of thought of experiment supporting that is that it's misidentified because if we're looking out into space and there are no stars in front of us, we've picked a little point in sky, there are no stars in front of us, and we look and we look and we look and we look, we keep looking, we see nothing. Then we conclude that it's dark energy that's that's driving things along, whereas there might in fact be a bit of dark matter there that we can't see, right? That's in our field of view anyway. So that's my prediction, and I'll explain on the record because I hope it's going to come true with James Webb Telescope. And there's also, look, while I'm here, there's also just a lot of other graphs, cosmological stuff. Anyway, so I had to jump over some stuff that actually demonstrated that Todd Desiato's radiative damping model is actually cosmologically compliant and lines up very well with what I just presented. Anyway, look, so that's it for me. For now, I'm done. If anybody wants to reach out to me, they can, and I'm happy to assist any way that I can. So that's it. That's it, Tim. We can move on. Yeah, he's not there. All right. Well, I'll keep you guys entertained then. Look, I'll just I will go through a little bit of detailed stuff here until Tim comes back. What I want to jump to and highlight is a couple of things. So here, I actually something that you saw before. I've got primary solution. We've also got secondary and tertiary solutions. So these are more SMOC with more of a SMOC flavour, standard model cosmology flavour. I can derive that. It's trivial. I've done that there. Right now, if you look at the results here, as I mentioned before, I can get multiple instances of the PDG result here. I can produce. It's easy for me. Right? I can produce it very, very easily. Right. But what I've done is I've actually discarded the secondary and tertiary solutions because they are not. And the reason for that is because they are not constrained. Because for the secondary and tertiary solutions, I'm plugging in. Right. I'm not plugging in. These solutions use data supporting SMOC data that is not constrained by cosmological microwave background radiation. So for that reason, I can discard the secondary and tertiary solutions because they're just too rough. So as far as I'm concerned, anything standard model of cosmology, it's rough. Right, it's a rough calculation as far as I'm concerned. It's not what I would call accurate. So anyway, I can produce their results, with very, very easily and to great precision if I wish to do so. But I had to try and chop some stuff out, so that's what I chopped out. Okay, so and here's a point that I'm making in the one of the detailed slides. But there are 3 flies in the ointment. These are not constrained by the CMBR, right? They're standard model of cosmology. These are standard model of cosmology stuff. It's not constrained by CMBR. Yeah, my stuff is, so I trust my stuff more than standard model of cosmology. Okay, so I'll move to. Okay, so here I'll cover off stuff that I wanted to talk about. I took out. I'm only going through this way, waiting for Tim here. So I've actually had a look at. Tim, you're back.
Yeah, sorry, I know. I never left. Yeah, no, I've been here the whole time, sir.
Oh, because I said to you that I was finished.
Oh yeah. No, I didn't want to interrupt because you jumped right into the.
Oh, sorry, mate.
So, oh no, that's okay. Well, yeah, I would say just keep going and running through it. Yeah.
Right.
Yeah. No, I heard you. You're like, okay, well, I'm finished. I was like, okay, I'm ready, and then you jumped right into a description of Todd's work and and some of the details. Okay. So yeah, I would say go for it, sir.
All right. Well, look, I'll just cover this off then. So I just want to shine a light on Todd's stuff because it's pretty good. So Todd's come up with a radiative damping model, and I'll leave it up to you guys to engage Todd and read about it, etc. But basically, what I do here is I show that Todd's zeta function. Well, this isn't exactly Todd's zeta value, right? So this is what I'm calling the dark energy damping factor. So Todd deals with the global value of zeta. I deal with it with its influence in the dark energy field. So I call it the dark energy damping factor because that's something I'm actually able to do. I'm actually able to separate out, for example, Puthoff's refractive index to the baryonic field, the dark matter component, the dark energy component. I can really break it down or just lump it all together. Anyway, I just want to highlight that Todd's radiative damping model, his zeta function lines up absolutely beautifully with this. Every time the cosmological constant is 0 and the speed of light equals the speed of light, his zeta value is 0 as well. And it lined up really, really well. So that's why I wanted to speak about it. And it's important for a number of other reasons as well. But anyway, look, here's a couple. Here are exact solutions that I've prepared for the dark energy damping factor for the present epoch for today. So you can see those exact solutions where I go where I can. I try and do exact solutions rather than numerical solutions. I always do numerical solutions, but anyway, here's the exact solution for the present epoch. You've seen that graph before. I spoke about that. Right, yeah, now here's something that important as well. So lessons learned. So Todd's, so again, I'm referring to Todd's radiative damping model, right? Now, I believe it's an important quantity requiring further research because I'm able to show that the end of the cosmological reionization epoch coincides with when zeta equals 1. And that's at approximately 1 gigayear, right? And the temperature of the universe at that time was 11.8 Kelvin. So these are the values that I've calculated, right? But it's important to emphasize that the SMOC, the Standard Model of Cosmology estimate for the end of reionization is 1 gigayear, and the temperature they say is 19 Kelvin, about 19 Kelvin. So my calculated results line up with the Standard Model of Cosmology expectation precisely. Here we have an exact value for the an exact solution for the asymptotic value of the dark energy damping factor. The next thing I sort of jumped over is my reference literature. So if you download the file, you can click on these. These all work. Sorry for the very small lettering, but I had to shrink it down to a small enough font size so that it wouldn't break the links. But anyway, you can download full calculations for everything here in the solution algorithms. Look, they're not easy reads, right? They're not easy reads, but look, I'm here. If anybody reaches out, I'll explain it to you. But anyway, that's just basically the algorithm that it's all done in MathCAD, and it's all there, and people can pull it apart and verify all of my claims, etc. So what else have I got here? Right, yeah. Now here are the graphs. I'll point out these graphs. Look, I explain the entire history of the cosmos in these graphs. All of the equations, everything anybody needs to verify for themselves is there, right? So I cover everything, the cosmological inflation process, everything. By the way, I should emphasize that the EGM construct organically derives cosmological inflation. It is not a band-aid that I had to put on, right? It just dropped out, and I was mortified. I was shocked when I saw this for the first time. So that's something else that I want to point out. Yeah, here we go, cosmological constant. Here's all the omega and you know, deceleration parameter and matter density parameter, etc. So these are all on the graphs. Lots of tables, exact, you know, very precise numbers there. So yeah, basically that's it. So look, just on this final diagram here, you'll see a way of representing, a good way of representing cosmology numbers, or my cosmology numbers. Just draw a circle, give it the radius of the Hubble length, you know, 14.57 gigalight years. Then everything on that surface, right, the perimeter of that circle is our universe, and it's observable. And those values line up with the numbers. So very simple trigonometry there. All right, Tim, I really am done now. I'm spent, I'm exhausted.
Okay, well, so let me do this then. Before we do anything else, Riccardo, let me see. I'm going to stop your screen share. I should apologize for the confusion. Yeah, I've been here the whole time. I've just been sitting listening to your presentation. So,
yeah, sorry, dude.
Oh no, that's okay. I think it was really valuable to go through all that material. So let's do this. I want to put this thing on gallery view, and everyone, please give a giant applause to Mr. Riccardo Storti. Riccardo, thank you so much. Thank you so much for coming back and presenting this. When you sent this to me, I got really excited about it. I was like, yes, this is awesome. This is, you know, because I think it's really important to look at the fundamentals of those models, right? And if we change those models slightly, that opens all these new worlds of possibilities. So thank you for coming back. So yeah, let's do this. I'm going to let everyone unmute themselves, and let's go into our Q&A session. And again, it's Option Y on Mac or Alt Y on Windows. And now that I'm here and unmuted and you guys can see me, you may see me sneeze. Just to warn you, I may sneeze, but I think I've got it under control. So, you know, who wants to go first? Who has questions? Go for it.
Yes, and I'm afraid I had internet trouble, so I came in a little late, Riccardo. But very interesting work. My first reaction is yes. You know, the speed of light being faster than what it is now in the initial expansion of the universe is, you know, I regard it as a really necessary condition, given the fact that the CMBR is remarkably uniform across the sky. I mean, we have photons meeting each other at Earth that have never been introduced, supposedly, and yet they are reflecting the same black body temperature. And I regard this, and correct me if I'm wrong, is this sort of analogous to the idea that a gravity wave will go at the speed of light, provided the space-time is not being warped very strongly. An analogy is, you know, shock waves in hydrodynamics, where you have a sound speed, which is for small, which is obeyed by everything for small perturbations on the pressure. But if you set off a block of TNT, or better yet, HMX, then the shock goes as fast as it wants until it slows down.
Yeah, so yeah, same, a very similar thing. So if
very good, very good.
Yeah, very similar thing. So
that's you know, I regard that as a one of the things that explains, well, I would enjoy your comment on the Albuquerque warp drive concept, where he believes he can kind of disconnect himself from space-time and be kind of a shock wave going as fast as he wants.
Yeah, look, I would disagree with that, because if you, what I tried to demonstrate in the presentation is in the Alcubierre situation. So, you know, if you put a pin through your spacecraft, so it's not moving because you're looking at it, it's not moving, but space-time is, right? What I try to demonstrate, so what I try to demonstrate is that the maximum that you can actually perceive space-time as flowing is going to be 1.1 c. So you can't go as fast as you like. You are cosmologically bound, and satisfying GR is not enough. So you actually need to be cosmologically compliant in your solution as well, and that cosmological compliance limit will be what looks like to you 1.1 c. But if you're standing on, if you somehow could be standing on the edge of the universe as it's expanding, that's where you measure c equals c. That's where you measure the definition of c. Everywhere else inside the universe, you're measuring, you're actually measuring a lower value. But even though it appears on your instrumentation like you're measuring c, that's because your instrumentation is inside the gravity well with you, right? So,
sure.
Yeah, and an important thing I just want to reiterate while we're on this point is the difference in perception between with GR, you're on the outside of it and you're driving your bodies and what happens in the situation. But in Cosmology, you're at the bottom of the map. So there's a big difference. Hang on. So have I just lost you guys? No.
No. I'm still here. Thank you very much for. I'll just make a comment. This sounds a lot like standard inflationary cosmology, where they.
Well,
only you're just saying let the speed of light vary rather than some scale size of the universe. Whoops.
Yeah, I think his connection might be a little bit unstable. I think he'll be back though.
The key question. I'm just kidding.
Well, we'll give him a sec. This,
Riccardo, we lost you there.
Yeah, Riccardo, your signal is breaking up, sir. Oh, and there he goes.
I didn't think my question was that crucial.
Yeah. Well, you know what? Let's keep the hands up. I mean, we can just chit chat for a minute. I'm sure that he will be back in.
There he is.
Is he back?
Looks like it. He's talking, but he's muted.
Oh, let me ask.
Oh, right. Okay. Sorry about that.
Okay. Yeah, perfect.
I don't know what happened there. Sorry about that. Okay. So we're good to go. All right.
Yeah. Okay. Well, John, did you want to ask your question again, or?
Oh, I just a very quick question, and then I'll let everybody else ask. Do you consider yourself kind of this is an inflationary model?
No, it's okay. So I described cosmological inflation, yes, and cosmological inflation just dropped out organically.
Okay, good.
Right,
good.
So I don't care one way or the other. It just dropped out, and it happened to agree with the standard model of cosmology. That and everything else agree with it.
Does this have anything to do with our embargoing our sanctions on the Russians?
No.
Pardon
Yeah,
me. I shouldn't even joke about that. Thank you very much, Ricardo.
No, it's all good.
And John, thank you as well, sir. Let me go to Robert next. Robert?
Hey,
Sir?
Ricardo.
Hey, Robert.
Hi, Ricardo. I think I answered my question, but I thought I'd just confirm it. You chose lambda as a cosmological constant. That has nothing to do with the lambda particle, because that's a baryon as well.
Yeah. No.
Just they play, just a symbol on words on play.
Yeah.
Okay. Oops, and there goes our signal again. Well, at least he was able to. At least he was able to finish the presentation.
Maybe
Yeah, well, that's right.
have him
Okay.
talk without the video part.
Pardon?
Maybe he can shut off the video so he has more data rate.
Yeah. Ricardo, would you like to try that? You want to try shutting your video off?
Yeah, look, I'm just going to try something else. Just 1 second. Let me just. You might lose me here, but it'll only be for a moment.
You know, I almost wonder if it might be Wi-Fi interference. Maybe I shouldn't admit this. I'm old school. I still use Ethernet. I don't trust Wi-Fi. I mean, I use it all the time for everything, but
Yeah.
I'm hardwired for this stuff.
Let me just.
Yeah, Ethernet's super reliable compared to Wi-Fi.
Okay. So I might lose you just in 1 second. Okay. Have you got me or not?
Yeah, no, you're still here.
Okay, all right. Well, hopefully this will give me a higher data rate.
Okay. Well, yeah. So did you want to respond to Robert's? I think Robert, you were just asking about the lambda term, right? But I think that's just a term.
It's just a symbol on word. Symbol on play. I just wondering. I think it's
Okay.
coincidence.
Why don't I go to Michael next?
Yeah, okay, we're good. So that should have fixed it, I think. I hope.
Okay, Michael, sir.
All right, sure. So my thought was, you mentioned the justification for a maximum warp field speed is because you could cross the cosmological event horizon and escape the universe. But I mean, doesn't the cosmological expansion constant already violate conservation of energy anyway?
No.
Why not? So you have dark energy and you have this energy per unit area, volume, that is being inserted over time or removed.
I'm sorry, Michael. I don't kind of follow.
So having a non-zero cosmological constant, having an expanding or contracting universe already violates conservation of energy, because all of your photons in your universe gain a small amount or lose a small amount of energy over time as that expansion or contraction happens. Yeah, you've got red shifting or blue shifting.
Yeah, but that doesn't violate. So you're saying it violates what?
So when you have expansion of the universe, or you have a accelerated expansion of the universe, your photons are red shifting over time. That's why the microwave background is microwaves instead of visible or something.
Yeah, and that violates what?
So that the energy of those photons has changed over time. They've lost energy as they've propagated all that distance through the universe. So that already, it violates conservation of energy over time so why would we?
No, that energy that's being lost. So you're saying, because I just want to understand what you're trying to communicate, that energy being lost by a photon means that the law of conservation of energy is wrong.
Well, no, I'm saying it's being violated in that for the cosmological constant in general relativity.
Yeah.
If you have redshifted light at a distance, it was emitted with a higher energy and then it got redshifted, and so therefore it lost energy.
It's
so that
been
violates.
Stretched. No, it hasn't. It's been stretched. right? So that photon's wavelength has been stretched, physically stretched over time. So there's an energy drop as we measure it, yes. But you're saying that violates, I don't understand. What?
So, well, I guess the more important question is, so why do you assume that nothing can escape the universe and therefore bound warp drive based on that?
Okay, so all right. Okay, it just, to me, right? Okay, my first bit of, I'll call it evidence, right? The first bit of evidence is just the escape velocity equation. So square root of 2gm on r, right? When you plug in my calculated value of cosmological mass and my calculated value for the Hubble length, right, which is my r. If you remember the circle that I might have drawn, that I drew in the detailed section, I draw a circle. It's got a radius of the Hubble length, right, and that's 14.57 gigayears, right? Now that's a value that I calculate. The standard model of cosmology value is almost exactly the same as mine. Now, if you draw a circle of radius r, and you calculate the circumference, you get all the standard model of cosmology values, right? But the point being, when you plug that value of r into the escape velocity equation, you come out with the exact solution is c, the speed of light in a vacuum. So that's the escape velocity for our universe. So that's the first bit of mathematical evidence that I provide. The
So
second bit of it,
if we could pause there, if you can hold that thought. So
yeah.
that also assumes that all of the observable matter in the universe is all of the observable matter, and that there's nothing outside of that's not observable. Because if there were additional matter outside which we can't currently observe, then there would be no net gravitational fields. It would not be isotropic. I mean, it would be isotropic. So you wouldn't have an escape velocity associated with that, because there's no well, so to speak, if matter just keeps going on infinitely.
Agreed.
But yeah, go ahead.
Yeah, agreed. So you picked up on an important point, absolutely, and I should emphasize that. What I'm suggesting is the only assumption that I can make is that what is beyond the observable universe does not exist. There is nothing. That's the only logical assumption anybody can make, because any other assumptions, I can come back at you and say, you're wrong. Outside that boundary are unicorns and puffy clouds, and I would be as accurate and as correct as the person saying it's something else. So the only conclusion anybody can make is what we can actually observe. Anything beyond that, there's nothing. All right. So that's, you picked up on.
Don't forget the dragons out there.
And the dragons. That's right. And you picked up on.
There be dragons.
That's right. There be dragons. That's right. It's a good point. Now coming back to the second bit of, well, I call it evidence. It's not really evidence. It's more of an opinion. Why we can't escape the universe. Now, why we can't escape the universe, in my view, withstanding that first bit of mathematical evidence, is that, to me, it just doesn't make any sense that we would be able to escape the universe. Because if we did, it would break physics, because that means the law of conservation of mass and energy. Well, it's wrong. And look, I don't know. It's maybe it's religious, but I believe in it.
So if there were counterexamples then to the laws of thermodynamics or laws of conservation of energy, then all bets are off.
I would have to rethink my position. Yeah, absolutely. Yeah, no doubt about that. At least the escape velocity conclusion. At the very least, that.
I can see Michael he's thinking about stirring the pot. Look, see that smile? See the smile? He's like, I'm
actually good for now.
Smile.
Okay.
I'm just thinking.
Well, thank you, Michael. So let's do this. Let me go to Harold Tavares next, then.
Oh, thank you. That was a great presentation. You gave a lot of beautiful, good information. Now, looking at my note, I want to ask you one question. Since I noticed you're using the speed of light to determine, the observable universe, the speed of light, and it looks like you assume that, you actually show that the speed of light actually is variable, have been variable throughout the cosmological history of the universe. And so the speed of light depends on the permeability and permittivity of the space-time. Now, are you assuming, in your model that the speed of light was variable in the past? Are you saying, is it variable in your model today, or is it just constant to what we measure the speed of light to be today? Because you throw some numbers there, making it look like, it's no longer it change, or will it change in the future?
Yeah, correct. So yes, the speed of light has been changing since the Big Bang, and it has gone up and down, right? The last time when the speed of light was actually the speed of light was when the universe had an age of 7.3 gigayears, right? And it also, that C equals C point also coincided with when the cosmological constant equaled 0. And that also coincided when the dark energy density parameter equaled 0. So what that means is that instantaneously, right, all of space-time everywhere at the same instant was more permeable to light than what it is today. So for us now, in a gravity well, in the bottom of a gravity well, the speed of light is 0.84 C relative to what it was when it was 1 at 7.3 gigayears, right? But that speed of light now, 0.84 C, has an upper ceiling of 0.92 C. So that upper ceiling is it's limited by dark energy, right? Because the dark energy field is not a massless field, right? A big chunk, 67% of the universe's mass is in that field, and the mass in that field is impeding the progress of light. Right. However, if we measure the speed of light in the laboratory with our instrumentation, our rulers and clocks have all shrunk, right? They're all scaled with the speed of light because we're sitting at the bottom of a gravity well. So yeah, that's it.
Okay. On your slide number 8, I notice you point out that at one time the speed of light was 1.37, etc., times 10 to the 38 than what it is today.
Correct.
Now, looking at the observable universe, the length would be 91.53 billion years. So what would the speed of light be, let's say, after the observable universe? Would it be higher because outside that limit, it seems to me like the permeability and permittivity of that space-time outside that length will be much lower, therefore the light would increase. What do you think it would be according to your model, of analysis? Would it be higher, lower, or the same?
Okay, it will be, so in the region that you're talking about that we can't observe, that's outside our universe, the speed of light in that region, in true nothing, the speed of light will be exactly C. It will be the defined value of C, because that's how we've defined C. So C, as I mentioned, is the speed of light is no longer a measurement, it's now a definition. That definition has been given a number, and that number is associated with very specific conditions. So it's got to be totally flat space-time manifold for that number to apply. But everywhere in the universe, it's not a flat space-time manifold, it's a curved manifold. Some places curve more than others, like black holes are curved more than here on Earth, right? So the only place where C actually equals C, which is the definition, is the region that you're talking about. And that will always be the value, because that's where it's defined.
Okay. Looking at that answer that you gave me, thinking about it now, it seems to me like you are defining the universe from your analysis that is equal to that is the infinity, that is an infinity, and those are the limits. Now, that's your model describe it, fitting, more like it is an infinity, like the standard infinity, or would it be like a transfinity, like George Cantor, an infinity within an infinity? But the model would be that even if this infinity with the values that you have now expand into the next infinity, like if it was a transfinity, an infinity with an infinity with, the mathematician, Cantor, would that be it, an expansion into the next infinity? It would all be the same. Is that what your analysis?
Yeah, actually, you've asked a really good question there. I've got to tell you. Okay, the answer is okay, and I might one day do a presentation on this, but I've actually developed that model. My model can be expressed in cyclic cosmology, and that's what you're talking about. One infinity moves into another infinity. So yes, and so yes is the short answer. So I go for the infinity becomes infinity becomes infinity. I go for that description, and that's cyclic cosmology. What I show in my work already, and if you know how to read my algorithms, I could point it out to you. But what I actually show is that when the very last photon, the very last photon expands, gets stretched to a certain point, to a certain length, if you like, it snaps, and at that instant you've got another Big Bang. So my work very much supports Roger Penrose's position on cyclic cosmology. Absolutely, yeah. So yes is the answer to your question.
Well, Harold, thank you, sir. Let me go to Michael, because we're starting to get down to the wire before John comes on. So, Mr. Boyd, go ahead, sir.
Hello, can you hear me okay?
Yeah, hi, Mike.
Hi, so I got 3 questions. The first question is speed of light. I'm kind of confused about what you're saying about being in a gravity well when we're talking about the speed of light. Are you suggesting that the speed of light is different on the surface of Earth than it is in outer space, for example?
Absolutely.
Are you saying the speed of light is less or more on Earth?
Okay, so on Earth the speed of light is reduced. So look, I'm very much a proponent of Puthoff's PV model, right? So yes, the speed of light is slower here on Earth than it is in free space. But our rulers and clocks are scaled, so we measure it as C everywhere. But it's not. It's actually different.
So when you make a measurement of the speed of light in outer space, say on the International Space Station, and they come up with the same speed as they do here on Earth, you're suggesting that's due to the time and the length being different?
Yes, correct. It's things are scaled accordingly. So our rulers and clocks are scaled accordingly. So that's why we always measure C as being C.
Okay, so are you also suggesting then that the space-time medium is different depending on where you are located in our universe?
Absolutely. Right. So let me. You've touched on a really good point there, and I'd just like to describe that. So everywhere in the universe, you've got the 0 point field, right? It becomes the polarizable vacuum field when you put a lump of mass on it, right? So like the Earth, right? So you transform the 0 point field by doing so, by putting the Earth there, you transform the 0 point field to the polarizable vacuum field. So what that means is, in a completely flat space-time manifold, you've got no matter in a universe, just the 0 point field, right? So you've got all these virtual particles popping into and out of existence. What you have in such a fictitious universe is you have an infinite spectrum. So the 0 point field is infinitely broad. You can have any manner of frequency there that you like, from very low to very high, right? In a universe with no matter, just a 0 point field, right? When you take our universe, for example, and you look at that, what you find is the 0 point field in the location of Earth is compressed. So when you put a pin in the Earth and you look at what happens at the cutoff frequency as you move out, what you find is this. You find as you move out, the cutoff frequency actually decreases from the surface of the Earth to whatever distance out into space. So your cutoff frequency actually decreases. But what happens is the number of modes increases. So what mass does, mass compresses the number of modes in the 0 point field spectrum from a very large number down to, in the case of a Planck particle, it converges that entire spectrum down to one single mode, right? One frequency.
One single what? Mole?
Mode, frequency.
Oh, mode.
Yeah.
Okay.
Frequency mode, right? So you've got this inverse relationship. So as you move out into space, your cutoff frequency for that spectrum decreases, but the number of modes in the spectrum increases. When you from outer space move towards the Earth, what you calculate is that the number of frequency modes in your spectrum is shrinking. It's getting smaller and smaller and smaller and smaller, but your cutoff frequency is getting higher. Right? So yes is the answer to your question. I would absolutely.
So basically the energy is the same then. You're just changing frequency and wavelength, correct?
When you say the energy is the same, what do you mean?
Well, wavelength, when you measure a wave energy, you measure the frequency and the wavelength and the amplitude, correct? So
well, yes, but so if you're talking about
so the energy, the amount of energy is the same, but the frequency and the wavelength are changing depending on where it's at, essentially.
Yeah, right. But see, look, just on the amount of energy, I'm not sure.
That kind of segues into my third question to you, which has to do with what's referred to as offset spatial divergence, which is essentially, to travel in space is to travel in time.
Yeah.
So if you are, for example, if you travel at a tenth the speed of light and you go for 2 light years away and come back to Earth, everybody's going to be dead.
Yeah.
Because of offset spatial divergence. So how do you account for this many body problem in your hypothesis?
Okay, I don't understand the question. Can you rephrase it, perhaps?
Well, I think you were getting at it.
Look, I totally get time dilation effects, right? I totally get that, but its relation to the many body problem, I'm not sure.
Well, there's not just time dilation. There's time can get shorter as opposed to longer, depending on if you're going in an accelerated frame. You can basically. It's like expanded space-time in Albuquerque's.
Guys, if it's okay to mention, we're starting to push into John's time. So
okay. So that's my question now, is about offset spatial divergence. If you don't think you can answer it, that's fine. I appreciate your answers so far. I was following you pretty well.
Good man. Thanks for that. Appreciate it.
Well, thank you as well. So let me see, Robert, if you can go quickly, let's do that,
Oh.
and then.
Thanks, Tim. I think this is quick. We know that the speed of light changes through certain materials, hence
Yep.
the bending of the beam. Can your theory describe that phenomenon, or at least apply it, or the philosophy of your theory?
Absolutely. In fact, you've raised a good point, because all of my work's based on the polarizable vacuum model of gravity by Harold Potoff, and that's an optical model of gravity. So it treats a gravitational field just like a lens. So it ties in exactly with what you're talking about. Absolutely.
Thank you. Thank you very much.
Wonderful. And Robert, thank you as well. So let's do this. Let's go to gallery view here. Everyone, please, one more big applause for Mr. Riccardo Storti. Sir,
Guys.
thank you. Thank you yet again. Thank you yet again. And I should apologize for cutting things short. A little bit of chaos today. But so what I'd like to do next is I want to introduce our next speaker, Mr. Dr. John Brandenburg, Physicist Dr. John Brandenburg, will be discussing the GEM, gravity electromagnetism theory that he's developed and refined over a period of decades. The GEM theory in its basic form gives a physical EM analog of gravity fields and evokes a Kaluza-Klein fifth dimension of subatomic size, but much larger than the Planck length. It yields a massless vacuum and a highly accurate formula for the G of the Newtonian gravitational constant. So without any further ado, let me introduce you to Mr. John Brandenburg. Sir, take it away.
Yes, thank you. It's a great honor to be addressing this conference. You'll forgive me. I just got back from a big trip, and the internet, of course, it shut down while I was gone, so I had to horse around with that. So I will try and get everything organized here. I haven't done one of these Zoom things for a while. Here, very good. Okay.
Yeah, and there is a green screen share button right at the bottom, should be bottom center of your screen.
Okay, yeah, very good.
Yeah. And then it'll make you choose the window, or if you have like a PowerPoint up, you can do that.
Yeah, unfortunately, this is a PDF. My boss had to, I have to submit everything to my boss to.
Oh, no, that's okay.
So he sent it back as a PDF, and because he said the original thing was too big. So as usual, I just got back from this trip. Very good. Let me share this, and
it looks great. Are you able to maximize that? It looks like it's kind of.
Yes, I can. Is that
there? Much better.
It?
Much better.
Okay. Here, let me go get up to the front here. I'm sorry. Like I said, I'm dealing with a PDF rather than a PowerPoint, just because of communications problems. So, yeah, the title of this talk, is an introduction to the GEM or gravity electromagnetism theory. I apologize for the name being kind of unimaginative, but I wanted it. I picked that name, by the way, in 1987. Other people have come up with their own GEM models and then retracted them. But I originally put this moniker on this concept back in 1987 at an APS meeting. Anyway, I'm at Kepler Aerospace, and first I'll do a brief introduction about myself, and of course we'll discuss the universe as it is, and then we'll discuss the Planck scale and Kaluza-Klein theory, the basic postulates of the GEM theory, which is a variation on the Kaluza-Klein theory. We'll discuss what I call the E cross B drift model of gravity. I'll explain what that all means when we get there. And the fifth dimension deployment and the Big Bang. Then I'll discuss the basic results of the gem theory, big G and the proton mass, and then I will summarize. This is intended to be kind of an introductory talk. There's much, I could go on for several hours about this. I've been working on this since 1987. So, but anyway, I'll tell you where I did my graduate work. It was Lawrence Livermore National Laboratory, a place called Teller Tech, a graduate school established by Dr. Edward Teller. And he would come and give us lectures. And it was very exhilarating. And I ended up working for Richard F. Post, who was the associate director for fusion thesis, and he was my thesis advisor. One of my thesis advisors, unfortunately, died while I was working for him. But there's me in the 70s. I have been a working plasma physicist now for since 1975, so really almost 50 years. And it's been a very wonderful field for me, especially once I originally started in plasma theory, but ended up branching out into experiments. And because the government wasn't interested in plasma theory, but one of the things I did was figure out how to reliably make air plasmas in microwave ovens. This is the center pictures the baseball coil at Lawrence Livermore. We were investigating mirror fusion. And here's, of course, trapped plasma in a mirror in the baseball coil. And then I also worked on, have worked extensively on plasmas for space propulsion. But what really concerns us here is a problem I was actually assigned when I was 11 years old by my father, who was a medical doctor. I asked him, I said, I'd like to become a physicist like my uncle. My uncle, William Surrey, one of the founders of Sierra Club, worked on the Manhattan Project in World War II and was just a wonderful fellow and very dashing. He worked at Lawrence Berkeley Lab. And he was my inspiration to become a physicist. And I walked up to my father one day while he was painting a fence, and I said, I don't know what I'm going to work on, specialize on when I become a physicist. And he said, well, you ought to work on Einstein's unified field theory. He said, if you're a dog, it's good to have a big bone to chew on, he says. So this begins really with Einstein. He tried for 30 years to unify gravity and electromagnetism. His rationale was that both followed the 1/r² law, and gravity waves, at least when they're in the weak field limit, travel at c, just like E and M waves. And of course, gravity runs the universe on large scales, but on what I call the mesoscale, R scale, electricity and magnetism are, of course, highly important. Of course, also they are important for the overall structure of the universe. Now, Einstein's problem was that even though he was one of the midwives, basically, of quantum theory, he ultimately rejected the quantum description of reality. He kept insisting that God does not play dice, to which Bohr responded in one of their debates. Bohr responded to Einstein and said, quit telling God what to do. My own take on this is that God may not play dice, but he does own a very fine casino. So But Einstein rejected quantum mechanics. And this, I think, was the crucial error that prevented him from really developing a workable theory of unifying gravity and electromagnetism. I then found myself as a young man in 1975, with a bachelor's degree in physics, starting graduate school at Lawrence Livermore Lab, which is an extension campus of UC Davis, and I was at Teller Tech. And Dr. Teller would come out and give lectures to us students. There were about 50 of us students, and to inspire us. And Dr. Teller related in one lecture that he had attempted to solve the Einstein problem of unifying the fields by using quantum concepts to try and fix the problems with Einstein's concepts. But he failed. Teller admitted quite frankly that his attempt was unsuccessful. And but his lectures, and particularly that lecture, inspired me to try as well. I remembered my father's assignment, basically, when I was 11 years old. And the fact that Edward Teller, who was a great man, would attempt this meant to me it was a respectable problem for a physicist to attack. And I know that Dr. Teller is still a controversial figure. I will simply say that he ran a fine school and produced a lot of good physicists. Great men are always controversial. Now, so there's where I was coming from. And now you know something about me. Now let us examine the universe in its most basic form. The universe as it is. 3/4 of it is now hydrogen. But it began with a big bang and about roughly 100% hydrogen with a scattering in of neutrons. Basically electrons and protons. And of course, everybody knows that if you leave a neutron in a box, after 10 minutes, half of them will decay into hydrogen with a neutrino. Now, the present universe has gravity and E&M as its long-range fields. Those are the two long-range fields we've been able to study. Quantum mechanics is particularly important at small scales relative to ourselves. The atomic scale, which is one end of the mesoscale where we live. Meso meaning middle, as opposed to the Hubble scale and as opposed to the Planck scale. Now, the basic parameters to describe the universe are, of course, then the proton mass, the electron mass, the speed of light, Planck's constant, the charge of the electron, the radius of the visible universe, roughly given by the Hubble time times c, and of course the Hubble time itself. So that's a back of the envelope description of the universe. Of course, the real universe is much richer than this, as this picture of these two interacting galaxies indicates. But the basic parameters it runs on are those that I have listed. Now, we also have, of course, quantum activity. And even though we don't have a theory that unifies gravity and E&M or gravity and quantum mechanics, we can look at the Planck scale. In a sense, gravity comes to the rescue of quantum mechanics, though it would break, many quantum physicists break out in hives to hear that statement, because the quantum vacuum uncertainty creates a ZPF, a zero-point fluctuation. And there is no cutoff to it at high frequencies. So technically, quantum theory gives an infinite mass for the vacuum, infinite mass density because of this zero-point fluctuation. What comes to its rescue is gravity, general relativity, because it says that you have the formation of black holes, which by quantum uncertainty appear and disappear, turning space-time into a foam of roughly the size, foam size of the Planck length. And of course, the masses of these black holes are Planck masses. And if you assume that electromagnetism is still active at the Planck scale, then you actually have a Planck charge, only in this case, it has blossomed from being just E to being 137 times, the square root of 137 times h bar c. So you have a Planck length, Planck mass, and Planck charge, and of course the speed of light. We're assuming, of course, all of this is operational at the Planck length, even though we can't access it experimentally. And as I said, this comes to the rescue of the quantum theory, which needs something to get rid of that infinity. Now, the fact that there's all this activity in the vacuum was very intriguing to Sakharov, the father of the Russian hydrogen bomb, and also the tokamak concept. And he attempted to use quantum mechanics to unify gravity and E&M, just like Dr. Teller. He did this in 1967. He produced a very interesting model. The gravity was due to a radiation pressure from the quantum ZPF. Now, that was not a new idea, that gravity was due to the radiation pressure of some kind of particles. But what Sakharov did was he said, using kind of economy of hypothesis, that the ZPF could supply, variations in the ZPF could supply the radiation pressure that would give a gravity-like force. And you could see that, but if you put two hot spheres, white hot spheres, let's say, in a dark box, they will repel each other if they're black bodies due to mutual radiation pressure. And the repulsion will be as a 1 over r squared. Now, if you put two dark objects in a bright box, the differential radiation pressure, if you stand on one dark object, one cold object, then you'll see a uniform brilliance all around you. The walls of the box are white hot, let's say. And all you see is a black dot in the distance, and that is the other cold body. And because of the black dot represents slightly less radiation pressure in that distance, the two spheres will attract each other with a 1 over r squared. Now, this sort of model has been around almost since the time of Newton. But no one could explain what the radiation was or where it came from. So Sakharov said, it comes from the ZPF. That the presence of matter disrupts the ZPF and allows a gravity-like force to appear. Now, he then used this concept to do an approximate calculation for big G, the gravitation constant between two masses in isolation in the universe. And he obtained big G as an integral over the ZPF. And because of the limits of integration, as it turns out, this formula works very well. It's c cubed times the Planck length squared O over h bar. And however, you must note that the Planck length is defined using G. So all this formula really does is say that the concept is self-consistent, the ZPF gravity model. It's not circular, it just makes sense. So, and it's very natural that Sakharov would come up with this model because a hydrogen bomb, as we're all aware, runs on the pressure created by setting off a smaller fission weapon inside a radiation cavity. They create so much radiation that a sphere of, or various shapes of hydrogen, of vessels containing hydrogen isotopes are then compressed, and the fusion reaction occurs. So it starts with fission. So the radiation pressure, or the, let's call it the Poynting flux, actually is key to the operation of a hydrogen bomb. So it's very natural that Sakharov would come up with this model, or find it a very attractive model. So that was Sakharov's contribution. Now, we know that gravity, of course, and E and M both follow the 1 over r squared law like optics. And we also know that the speed of light seems to be shared by gravity, weak gravity waves and E and M waves. Or at least theoretically, we don't actually have a speed measured for gravity waves yet. But there's another very interesting piece of evidence that gravity and electromagnetism are related at a very deep level. And that's the Dirac large numbers hypothesis, which says that basically, if you take a composite mass, or the force of gravity between a proton and an electron, and I'm using CGS units simply because I hate writing 4 pi mu naught and epsilon naught all over and over. If you have the ratio of the forces between a proton and an electron of gravity and electromagnetism, here listed as CGS units, then this approximately equals like something within a factor of 10 to the classical radius of the electron divided by the Hubble radius. And when Dirac first published this, he was widely criticized for it, that this was some kind of numerology, and of course it led immediately to ideas that G might be varying with the age of the universe, but something far more subtle is apparently going on, because G has been measured using orbits of spacecraft, particularly around Mars. Ronald Helling, one of my old professors, showed that G cannot be varying at the rate that this equation suggests as the universe expands. So there was another interesting thing about this. It comes out to be 10 to the minus 40. Of course, that's in base 10. But this number 40 and 43 kept coming up. And what was interesting was in graduate school, I discovered that you can derive this relationship, the Dirac large numbers hypothesis, if you equated two numbers, one of course was big omega, which is the parameter that gives the gravitational closure or openness of the universe, which sits at approximately 1, right at the critical thickness, critical density, and which is a great cosmic coincidence and caused the invention of the inflationary model. And then there's also a curious thing is that the universe is optically critical to Thomson scattering. Thomson scattering going as the Thomson cross-section. It's the scattering of lower frequency E&M waves by individual electrons. Assume the universe is full of plasma. And it goes as 8 pi n divided by 3 to the radius, the classical radius of the electron squared. So that also equals 1. And if you equate these two, you discover that the density kind of cancels. So at least for a universe similar to our own or somewhere close to the critical density, you can imagine that the gravitational coupling of the universe seems to be controlled by the electromagnetic coupling of matter in the universe. To show you what I mean, here's an optically thin natural gas flame. It doesn't cast a shadow. On the other end is a candle flame that's full of carbon particles, and it does cast a shadow. You can test this for yourself with a butane lighter and a candle. As it turns out, the universe is slightly misty. It's optically critical. It's very close to the critical point. And for instance, if the universe was optically thick, then we would have Olber's paradox. We would have a sky that was so full of stars that everything in the universe would be cooked. In other words, the universe would be one, you look out at the universe, it'd be one solid stellar surface. Or if it was optically thin, in one extreme, you'd look out and not see really any other galaxies at all. But you see lots of them. And in fact, if you do a deep sky survey, you'll find that eventually the galaxies all pile on top of each other. You go to what's called a confusion limit, and you get a blue haze. The sky, the deep sky in its deepest look is like a blue sky in summer here in Texas. So if one takes those concepts and equates them, that the gravitational closure is somehow correlated to the electromagnetic coupling of the universe, then you find the Dirac large numbers hypothesis falls out. And we'll leave aside its physical meaning for right now, but the large numbers hypothesis suggests that whatever the past or future of the universe, it looks like gravity and electromagnetism are intimately related, because the coupling of matter through one field is also seems to correlate with the coupling of matter in the other field. Now, the important quantities from the Dirac large numbers hypothesis are this composite mass. The universe seems to like this number. You can look at it as a a composite mass, which is the geometric mean between the mass of the proton and the mass of the electron. And we'll call that the mesoscale mass. And then, of course, if you combine that with E squared and C squared, you get a classical radius that's about 42 times smaller than the classical electron radius. And also, of course, the relationship between these numbers is something around 10, like a square root of the fine structure constant, let's say. So this number, E squared over H bar C, and that should be an H bar there, pardon me, is 137. So now, the universe as it is has this important problem that despite the fact that the gravity theory, general relativity, has rescued quantum mechanics from a complete catastrophe involving infinite mass in the vacuum, it still leads to a titanic mass density in the vacuum due to the Planck length, the Planck scale. And that's 10 to the minus 96, 10 to the 96 power kilograms per meter cubed. That's, I believe the whole universe only is 10 to the 54th. So kilograms. So this is a lot of mass density. And of course, if that was true, we wouldn't be having this conversation at all. So where is this mass density? This would be kind of the a measure of the cosmological constant. And we know that rather than being very large, the cosmological constant is very tiny based on measurements. So that's the universe as it is. Now, let's try and explain this universe that we are in. And a very important contribution was made by Theodore Kaluza and Oscar Klein. Theodore Kaluza being from Germany, Eastern Germany, and Oscar Klein being from Sweden. And they found that they could, by adding a kind of inert fifth dimension, that if you stuck with 4 dimensions and did the Hilbert action principle, then you got the equations for general relativity. But if you then added a 5th dimension, you ended up with not only the gravitational equations of Einstein, general relativity, with the electromagnetic tensor as a source term, but you also ended up with Maxwell's equations, plus a massless scalar equation. Very interesting. This reminds me, of course, of Tesla's belief that he had found scalar electromagnetic waves of some sort. But anyway, we'll leave that controversial subject to some other time. So anyway, with just by adding a 5th dimension, you can get the equations that describe basically the long-range forces of the universe, general relativity and Maxwell's equations. And what's interesting is the only constraint on the 5th dimension size, on the 5th dimension is nothing really depends on it. Its size is unspecified and its size doesn't really enter the equations. So this is why people can talk about the 5th dimension size as being either somewhere between the Hubble radius and the Planck scale. Most people think it's down around the Planck scale. As you will see, I think not. So anyway, Kaluza-Klein theory adds this wonderful 5th dimension, and in just one bold stroke gives us Maxwell's equations plus general relativity. Now, here's where I entered the scene. The GEM theory is based on two postulates. One is that gravity fields are equivalent to arrays of E cross B drifts, or pointing vector drifts, pointing vectors of quantum ZPF of the Planck scale. Now I'll show you what the E cross B drift physical model means in just a minute. But also the second postulate is that gravity and E and M exist as separate fields along with protons and electrons due to the existence and deployment of a hidden fifth dimension from the Planck scale. In other words, you start out with just gravity and quantum mechanics to give you the Planck scale, and somehow a fifth dimension deploys from the Planck scale, becomes much larger, kind of like an inflationary model. And you end up with a universe with protons and electrons in it instead of Planck masses. And you also end up with a universe that has electromagnetic fields in addition to gravity fields. So what we will find is that the GEM theory leads to a mechanism for the vanishing of the ZPF mass density. And also an accurate expression for the Newton gravitation constant based on other parameters of the universe. And also, and I'm not going to discuss this in this talk, a vacuum Bernoulli equation for lift and gravity fields related to propulsion. Now, I'm a plasma physicist, and one of the first things you learn in plasma physics, confining plasmas in magnetic fields for fusion, is a phenomenon called the E cross B drift, where if you have two charged plates, plus and minus, and a magnetic field running parallel to the surface of the plates, so that the electric field and the magnetic fields are crossed, then if you drop any charged particle in, a proton, an electron, a charged zinc nucleus, even a sweater pulled out of a dryer on a cold winter's day where you didn't use a fabric softener pad, so it's charged with static electricity. They will all end up drifting in the same direction, regardless of charge and regardless of mass. They'll all end up drifting in the same direction at the same speed. And I remember just being mystified by this. How could a configuration of electric and magnetic fields create this phenomenon where suddenly all charged matter, and of course in the standard model, all matter is charged down to the quarks. All the quarks are charged, and so is the electron. They all end up moving at the same velocity in the same direction. Now, this drift is well known in plasma physics, but not elsewhere. Oh, pardon me. Now, you can do a lot of tricks with the E cross B drift. If you have just two parallel plates charged at plus and minus, the velocity of all the charged particles, including quarks and things like that, is uniform. But if you put some curvature in the system by making the plates at an angle, then all of the charged particles accelerate in the same direction at the same rate. And this leads to another thing you can do is vary the electric field between the plates, and you'll get the same effect. The charged particles will all accelerate at the same rate in the same direction. And you could simulate this. Here's a simulation of two plates and a magnetic field coming out of the screen. And I've dropped an electron and then a heavy electron, like 10 electron masses. And you can see that they're both accelerating. Their motion is kind of complicated, but they're both, as we call it, the guiding center of their motion is the same direction at the same acceleration. And in the limit of very strong magnetic fields, like down at the Planck length, you could imagine that the individual motion of the particles, their detailed motion is no longer discernible. It's lost in the quantum noise. So this is a physical model of gravity, but it's purely electromagnetic. And that works for particles in free fall. Pardon me, I'm working with a PDF here. And then you can go to the limit where gravity is a force, just like any other force. Holding your drink bottle down to the tabletop because of the Poynting vector, radiation pressure. So this model is most easy to derive for the limit of E over B much less than 1. In other words, E cross B drifts speeds that are small compared to C. But it can be generalized to a full covariant form. Gem gravity produces a very interesting phenomenon called self-censorship of the ZPF mass density. The E cross B drift model of the Newtonian potential is E squared over B squared times the speed of light squared. This is in CGS. And if you do a covariant generalization to metric form from the Newtonian potential, you get a metric tensor that is a normalized form of a part of the E&M stress tensor. It's a true tensor, varies covariantly, and so does the denominator, which is B squared minus E squared down to the Planck scale. Now, if one takes that covariant generalization and reinserts it back into the definition of the E&M stress tensor, T alpha beta over here on the right, then one gets the amazing result that the ZPF contribution to the vacuum density vanishes. It censors itself. And this means that the vacuum does truly weigh nothing when looked at from a quantum mechanical perspective. What it also says, interestingly enough, given this definition of the metric tensor from the gem theory, as part of the electromagnetic stress tensor, basically normalized, is that magnetism dominates at the Planck scale. That B squared minus E squared is not 0, but in fact, B squared dominates, indicating kind of like magnetic monopoles are present. Interesting subject to pursue, but we'll just leave that for right now. Just say that the basis of the vacuum, the fabric of the vacuum is electromagnetic, but it's mostly magnetic. Now, so we have from the first postulate an electromagnetic model for gravity fields. It can be made fully covariant. That was the first postulate. I like doing things with postulates because that's what Einstein did in his general theory of relativity, his theories of relativity. Now, the second GEM postulate is the fifth dimension allows the separate existence of, or let's say the separate detectability of electromagnetic fields from gravity. We all know what lightning is, and magnetism holds our kids' report cards to the refrigerator door. And gravity, of course, keeps the refrigerator on the floor. Now, those are very easy to separate effects at the mesoscale. But at the Planck scale, we imagine that they were all congealed together into one force field. But let's say that when the deployment of a new hidden dimension to a standard length of R0, which is E squared over M0 C squared from the Planck length, not only creates separate electromagnetic fields phenomenon, let there be light, but it also says, let there be hydrogen. The Planck masses shrink from being Planck masses to the masses of the protons and electrons, but they also split into protons and electrons. Now, part of this is, you got to remember that charge can be written as a distance. Charge times a charge to mass ratio can be written as a distance, like a classical radius of a particle based on its charge. Charges are the electron. Let's call that Q sub t, and quarks. Now, let's say that the time-like part of this Minkowski, this image of Minkowski spacetime of charges distance, E is the electron charge, is the time-like part, and the three quark charges are the charges of kind of three components of charge: Q sub x, Q sub y, Q sub z, for want of better terminology. The deployment of this from the Planck scale, from everything being the Planck charge, conserves charge so that the sum of the charges is zero. But what it also does, it also conserves the space-time light-like interval. In other words, the quark and electron charges form an image of Minkowski space-time that is light-like. So Q sub t squared minus Qx squared plus Q. If we take the standard quark model charges, 2/3 E, 2/3 E, minus 1/3 E, we square them, then they add up to 1. And so, to the best of my knowledge, I'm the first person to have pointed that out. It came out in about 2010 in a paper. So now, what's also interesting is the ratio of this hidden dimension size to the Planck length. because it's correlated with not only the deployment of this fifth dimension from the Planck scale, but also the separation of the proton and the electron, that the logarithm of this will turn out to be related to the square root of the mass ratio. And you'll see in a minute what I mean. The logarithm of this definition of R0 related to the ratio to the Planck length does equal this number 42.8503. Yes, like Hitchhiker's Guide. And I believe it or not, I was not aware of the Hitchhiker's Guide when I started this theory and derived this number. So I came up with the idea and then found that if I checked it, the numbers were very, very close. Now, a key assumption is that quark confinement continues at the Planck scale. The deployment of a new hidden dimension to length R0 from the Planck length also separates protons from electrons, and assume that the quark confinement, the quantization of charge at either 0 or E, that is still operative down at the Planck scale. So what this means is we can treat even though the proton is a composite particle, we know that from all sorts of experiments, that there are three quarks in there, three partons, as they call them, that the proton behaves as a fundamental particle in this context. And this is anathema to a lot of people. They've also told me that hydrogen is boring and they don't want to study it because the particles are stable. But the gem theory leads immediately to you have to have a mass model for how this occurs. And it turns out the mass of the particles depend on M0, this mesoscale mass, a composite mass at our mesoscale of the mass of the proton and the mass of the electron, times an exponential factor, which is really just the mass of the proton and electron mass ratio square root, with the sign of it depending on the normalized charge of the particle. So that Q sub E equals 1, proton, mass is the proton. Q sub E equals negative is the mass of the electron, smaller. And of course, this leaves M0, which blossoms from the, or rather shrinks from the Planck scale of the Planck mass. And it shrinks according to the same formula with the Planck charge. So, and there should be a negative sign in there, pardon me. So anyway, the Planck charge scale shrinks with the deployment of the fifth dimension to larger size and becomes the mesoscale mass, or this composite mass, mass of the proton, mass of the electron, the geometric mean of that. And it depends on the Planck charge, h bar c, the square root of h bar c. Excuse me. I thought I turned this thing off. Excuse me. No one ever calls me unless I'm doing something like this. So now, the Kaluza-Klein theory of the gem requires field quantities to be independent of the hidden dimension and for its size to be small. Now we've chosen this mesoscale size, R sub 0, and it depends only on hydrogen, only on mesoscale quantities. The parameters of hydrogen that we see in the universe. And we can imagine that we are going to allow subdimensions like the quark charges, can be X, Y, and Z, let's say, in some abstract sense. Now, where did we get this idea? Well, the second postulate is based kind of on Big Bang phenomenology. Let's imagine the universe when it first existed as being kind of a Planckian vacuum, gravity and space-time, with its EPS vacuum, quantum gravity and quantum mechanics. And then the Big Bang occurs, and you go from 4 dimensions to 5 dimensions. And not only does E and M appear separate from gravity, but so do particles that we know, protons and electrons, that are stable. So, economy of hypothesis suggested to me, or that concept suggested to me, that the two effects were correlated. That the appearance of E and M and gravity as separate fields also correlated with the appearance of the proton and the electron from the Planck scale, particles, Planck and anti-Planck particles. And so this would all kind of work. You would end up, you start out with a Planckian vacuum and end up with a universe that, at least to first approximation, looks like the universe we experience. Now, what is exactly this ratio of this of this mesoscale size, or this hidden dimension size, and the ratio of that to the Planck scale? Well, as it turns out, because of the numbers we have chosen for the size of the Planck scale, this M0 being the composite mass of the proton and electron, it turns out it's the ratio of the quantum E and M interaction between the proton and electron electrostatically and their gravitational interaction. In other words, quantum mechanics is central to gravity E and M unification. And as we know that in the case of hydrogen, that quantum mechanics suppresses radiation. In other words, if an electron and proton are close together, alpha, which is a factor which diminishes things, 1 over 137, means that the interaction must proceed by photons, emission, and absorption, and that this produces kind of a suppression of radiation, a suppression of the force. So, pardon me. There. Now, so we find that this ratio, here is the model, that the proton and electron, the ratio of their masses is related to the logarithm of the separation of the ratio of the mesoscale size to the Planck length. So that as this goes to 0, this goes to 1. Or as this, let's say this goes to something very close to the Planck length, this will go to 1. The proton and the electron will merge and become part of antiparticles of the Planck mass. down to Planck scale if you squeeze this system down to the Planck scale again. Now, because of this expression, you notice sitting there is big G. And we defined all these quantities, so we can actually invert this expression and obtain a value, theoretical value from this model, or the Newton gravitation constant. And its form is quite interesting. It depends on the quantum, the composite mass that appeared in the large numbers hypothesis. And of course, the electronic charge. So the gravity constant is basically a charge to mass ratio squared. It also depends on alpha, indicating that gravity, as in the E cross B drift model in the first postulate, is mediated by quantum electrodynamics. And of course, then there's this exponential factor. So this is the number that emerges, 6.6724. And this has been verified. You can check it at this by Lance Williams at his Confluence Institute. And he posted it on his website. A very, very talented individual. And he's an expert on Kaluza-Klein. Now, this is the actual value, at least last time I checked, 6.67418. So we're dealing with close to part in 10,000 of accuracy of this formula. And it says basically that G depends on the existence, the gravitation constant is really dependent on the electronic charge and hydrogen masses in quantum mechanics. So the gem theory provides, and it is the only known accurate formula for G that is derived from a physical model. I mean, people can sit there on Sunday afternoons and come up with combinations of pi and alpha and everything like this, and come up with something close, especially if they're allow themselves a diddle factor or here or there. But in terms of deriving it from a physical model, I am the only person to do that. I'm not trying to sound immodest at all. But let me tell you something. If someone else could derive the value of G from some kind of physical model, you would have heard about it. If that model produced anything accurate. So the gem expression for G confirms that gravity, as in the first postulate, is based in quantum electrodynamics, as in the first gem postulate. And that's the signature, is that alpha, the ratio of Planck's constant to electronic charge squared, sits right in the center of the definition of G. The rest of this is just from and all of this is just from the universe as it appears, with electronic charge and the mass of the proton and electron. So gravity as a separate field from electromagnetism is due to this deployment of the fifth dimension, which I also think kind of really created the Big Bang. So there's some other details that can be, I've glossed over here. It turns out there's some perturbation theory related to the fact that we want everything to go to the proper limits at the Planck scale, not just be close. But anyway, we end up with a mass model for the proton mass in terms of the Planck mass. So it goes according to the normalized Planck scale charge. And also there's a perturbation due to radiation fields. And this goes as 1.66 times a minute. So very close to the actual measured value. So people have derived the mass of the proton from quark models now to within a few percent, but this is even closer. So anyway, in summary, Einstein was right. He was a smart guy. Gravity and E&M can be unified, but quantum mechanics must be used. GM unification theory is based on two postulates: the E cross B drift model of gravity and the Kaluza-Klein fifth dimension deployment to a certain size, R0, based on hydrogenic quantities, so that hydrogen and E&M fields appear in a correlated fashion. And this leads to formulas linking the metric tensor directly to the E&M stress tensor, which give us a vanishing ZPF mass density. This also leads to highly accurate formulas for big G and the proton mass. So our goal is, of course, eventually to go to Mars. And at Kepler Aerospace, here we are with our moon base. So we're thinking about the future. Thank you very much. And I'm sorry I've run over my time a little bit, but let's, we certainly have time, plenty of time for questions. And
Yes.
Yes. So let me, let me get out of this mode so you can see my face again. Oops.
Oh, that's okay, John. So John, let me remove the spotlight there, and I am going to stop. I'll stop your screen share for you. So again, before anything else, I want to put this thing on gallery view. Everyone, please give a giant hand to the indomitable Dr. John Brandenburg.
I'll tell you, the COVID almost got me. COVID Delta. I spent 4 months in the hospital.
I know. So many people
I
have
was
gotten
knocking
COVID.
on heaven's door by God's grace, though I survived. And I'm here giving you this talk.
John, thank you so much. Thank you so much. Yeah, and I'm struggling with allergies today. That's why I keep blanking out the camera. That way you guys don't have to.
Hey, I've got them too.
Yeah, you guys don't. You don't have to watch me sneeze that way, right? So let's go to our Q&A session. And yeah, I'm GEM model. I mean, this is one of the big ones. So I'm really excited to have you here. So again, that's Option Y on Mac or Alt Y on Windows to raise your hand. And let me see. I'm going to allow everybody to unmute themselves, but go ahead and please raise your hand if you have a question. And Mr. Vallone, well, welcome back, sir.
Thomas Vallone. Yes,
Dr. Vallone. My apologies.
Dr. Vallone.
Tom, you're muted.
All right.
Okay.
Hopefully you can hear me.
Yeah, I can.
I've been waiting years to hear this lecture. Every time.
Oh, no kidding. I'm very honored that you would say that.
and I almost got you as a speaker to actually give this lecture at our conference on future energy years ago. But
oh my God. Okay.
Work out. So it's okay. I'm finally.
It all works out.
Rewarded by sitting here and.
I'll appear at your next one. I'll be happy to zoom into your next.
Yes,
one.
poach our speakers, please. Tom, poach our speakers.
Okay.
If you would like a list, I can provide you with a lengthy one, sir.
Sounds good. Well, I had some questions, and
sure.
The first is, when you started off, I was actually thinking that you're going to include Puthoff's famous.
Yeah, and I'm sorry, I glossed over that. Puthoff, Hal Puthoff is a friend of mine.
Yep.
And he, I think he made valuable contributions to the Sakharov model of ZPF.
Right. Yeah.
And of course, he's he's always been on the front lines of, let us call it phenomenology.
Well, he uses the stochastic approach to.
Yes, he does.
And that's really exciting to see how simplified those papers of his and also the two other associates that were.
No, I salute Hal Puthoff for his contributions to this with his SED theory. I'm sorry. I basically, this is a kind of a talk given to mainstream physicists who don't like SED, so I put in QED instead.
There you go. Well, the basic question I have about that is, how are the two related? Because obviously his approach is quite different. He's including the ZPF, and then he does the E cross B effect, and it's like the low frequencies, I believe, and then inertia of the separate paper in PhysRev is the higher frequencies of the universe.
I've looked carefully at his theories, and I find that my theory is basically kind of a limit of his theory, except the hydrogen and proton masses don't enter into his theory.
Ah, interesting.
It's the second postulate, the deployment of the hydrogenic system, the proton and electron. That's one of the keys, and he didn't go there.
I see.
And judging by the reaction of some mainstream physicists at conferences, I can understand why. I gave a paper at the Division of Particles and Fields. They gave me a poster. And I was terrified, deeply terrified that I was going to be ignored and put off in some far corner of the auditorium, drinking my beer and minding my poster session with nobody coming by. But to my delight, I was met by a mob with pitchforks and torches instead.